Hi everyone. In the last video we talked about acid anhydrides, and in this video we're going to discuss esters, which is another group of carboxylic acid derivatives. So let's talk about how to prepare esters. There are a few different ways to prepare an ester. So you can start with an acid halide and end up with your ester. In this reaction, you do have a byproduct of hydrochloric acid. In another reaction, you can use an acid anhydride to create an ester. You could also start with a ketone. Or a carboxylic acid. And with our carboxylic acid, there's actually a couple of ways that you could end up with that ester. So I'll draw two arrows there. So see if you can figure out the reagents you would need to create these esters from our starting materials. So you can pause the video, try it on your own first, and then we'll go over it together. Okay, so how would we turn an acid halide into an ester? We would use an alcohol. And then we would also want to add pyridine in there, which I abbreviated PYR, because hydrochloric acid is a byproduct in this reaction, and that can react with any acid-sensitive groups that might be present on the rest of our acid halide or ester. So we just want to remove that from solution. What about our anhydride? How would we create an ester from that? Also with an alcohol. Now our byproduct here would be acetic acid, which isn't as strong as hydrochloric acid. So we don't have to worry about it as much, so we don't really need pyridine for that second reaction there. What about our ketone? How do we turn that into an ester? We use a peroxy acid. So that one is slightly different. So notice that we're just kind of squeezing an oxygen in between the carbonyl group and one of the alkyl groups there. And then finally, how do we turn a carboxylic acid into an ester? Well, we could use an alcohol, again, with some acid to protonate, or we could use sodium hydroxide, and that would deprotonate the carboxylic acid. And once that oxygen is negatively charged on the carboxylic acid, we can then use an alkyl halide. And the negative oxygen would attack the alkyl halide. And so that would be our R group that's on the ester. All right, so again, we've covered most of these already. So not much new that we're learning here, but let's talk about some of the reactions we can perform with esters. So the first one is acid hydrolysis. So this is essentially the reverse reaction of a carboxylic acid forming an ester. So here we're going to start with our ester, and then we're going to use water and catalytic acid to turn this into a carboxylic acid, and then our byproduct is an alcohol. So the water tells us that we have hydrolysis. The catalytic acid makes it acid hydrolysis. All right, so notice that we're at equilibrium here for this reaction. So how could we put stress on this chemical equation or reaction in order to favor the product. Well, remember, Le Chatelier's principle tells us that we need to put stress on either the reactants or the products. So one way that we could favor the products is by using more starting material. So we could just flood this reaction chamber with water. So that's one of the reactants, and that's going to kind of force the reaction to the right towards the products because we have so much of our starting material. And so the reaction wants to reestablish equilibrium. The other option is we could remove one of the products as it forms. And that's going to put stress on the system, and the system will want to create more product as a result so that it can reestablish equilibrium. Now, in this case, we'll probably remove the alcohol. And one way we could do that is through distillation. Because alcohols tend to have pretty low boiling points. Remember, ethanol, for instance, has a boiling point of 78 degrees Celsius. There's another type of hydrolysis that we can perform called base hydrolysis. So again, we start with an ester, but this time we're going to start with a base, our hydroxide. And the hydroxide is going to attack the carbonyl carbon, and then we end up forming a carboxylic acid. Now, the hydroxide ion is a really strong base, so it is going to deprotonate the carboxylic acid that we form. So we're going to have to reprotonate it with some acid in the second step. Now, one example of this base hydrolysis reaction is something called saponification. And you might have heard of this before. This is how we make soap. So you start with a triglyceride. Oops. Keep hitting the next button. And if you're taking biology, you might have already heard of triglycerides. Also called fat. And then you're going to react this with a base like sodium hydroxide. And what you end up with is something called glycerol, which has these alcohol groups attached, and carboxylate salts. So you might have sodium ions in there balancing the charge, but the carboxylate salts would be our soap. So that's pretty cool. If you've ever made soap before, this is essentially the process that you were performing. Now, the next reaction that we can perform with esters is called Esterification. So that's a very long and fancy word. But we start with, again, our ester. Surprise, surprise, I know. And we're going to react that with an alcohol. We're also going to use catalytic acid again. And our products will be another ester and another alcohol. So what's going on here? What's the point of this reaction? Well, let me highlight a few things here. So in the beginning, we have two different R groups, right? And two different oxygens that are attached to those R groups. So I'm going to highlight one of these alkyl groups in blue, And then I'm also going to highlight the alcohol or the alkoxy group on the alcohol, because they're actually going to switch places essentially. Actually, I meant to also highlight the oxygen on the ester. I apologize. But those are going to switch places. So the blue groups are going to end up in the alcohol, and then the red groups are going to end up in the ester. Oh, there we go. So for instance, maybe you have an ethyl group attached to your ester and you want to switch it with a methyl group. You could do it through this reaction. Okay. And let's actually just write that down. So maybe we have an ethyl group attached, but then we react this with methanol, so that would be CH3OH. So at the end, we're going to end up with a different ester and a different alcohol. So this is why it's called trans-esterification, because we're switching our ester around. We're translating our ester into something else. Okay, so next, let's talk about aminolysis. So you can probably guess what we're going to do here by the name amino. We're going to start with our ester and react this with ammonia. And this is going to form an amide. However, this is a really slow reaction, so it's not a great reaction. If we need to form an amide, we would probably use a different reaction, like with an acid halide, for instance. And part of the reason this reaction is so slow is that the ester is a weak electrophile. So the ammonia molecule doesn't really want to attack it very quickly. So we try to avoid this reaction if we can. But it's still good to know about because you never know, it might come in handy. All right, so let's talk about reduction. How would we reduce an ester? Now, I know we're talking about a lot of reactions in this lecture, but many of them are pretty similar to other reactions we've talked about. And we'll go over the reaction map at the end. So don't worry, we'll summarize all of this. Okay, so if we reduce an ester, let's say with lithium aluminum hydride, and let's use excess of that, followed by acid, we're going to form a primary alcohol. Now, what if we only want to reduce our ester once and form an aldehyde? Unfortunately, we cannot isolate this aldehyde using lithium aluminum hydride, similar to what we've talked about before with our other derivatives. We need a special reducing agent. So this would not even stop at the aldehyde, it would keep going to the primary alcohol. Now, you might be wondering, why don't we use that lithium triterbutyl aluminum hydride? Well, unfortunately, we need to use something different with esters. So with esters, we're going to use the following. We have aluminum and hydride, but bonded to that are two isobutyl groups. So this is called diisobutyl aluminum hydride. So this is abbreviated as DIBAL-H. Or sometimes you might just see this abbreviated as DIBAH. Kind of depends on the source, but you're essentially just using the letters in your molecule here. So DIBALH. But not everyone uses the L. So one example of this type of reduction, if we have our ester and we reduce it using this dibol, it's kind of a funny word. We follow that up with water. This is going to create our aldehyde. So if you ever need to turn an ester into an aldehyde in one of your syntheses, or just ever in general, you would use this diisobutyl aluminum hydride molecule. Okay, the last reaction I promised that we're going to cover for esters is what happens if we use a carbon-based nucleophile. So for instance, a Grignard reagent. So let's start with our ester, and let's react this with a Grignard reagent. This is going to initially form a ketone because we're going to add that R group once, but this reaction keeps going. The ketone is actually really electrophilic compared to the ester, so it's going to keep reacting with any excess Grignard reagent. So this is hard to isolate as well. So let's just make a note. This ketone is more electrophilic than ester. We'll keep reacting. Okay, so let's show what happens when it reacts with more Grignard reagent. And again, that's typically followed up with water to protonate. This would form our tertiary alcohol. Okay, so in general, when your starting material has a leaving group, like an ester does, so OR is our leaving group, the Grignard reagent is going to keep attacking our carbonyl carbon. All right, so again, when your starting material has a leaving group, which most of our carboxylic acid derivatives do have a good leaving group, then the Grignard reagent will just keep reacting or keep attacking the carbonyl carbon until it can't attack anymore. So that typically will result in that tertiary alcohol. All right, so let's summarize everything we've learned in this lecture. I know it was a bit of a long one, so thank you for bearing with me here. But let's start with our ester in the middle. And I'm going to draw different products or starting materials around this ester, and I would like you to try to fill in the reagents that we would use to form all of these different products, or how to get from a starting material to the ester. So for instance, we have a carboxylic acid, which there are actually 3 different ways we could form our ester. I didn't include one of them earlier, but see if you can figure out the third one. And then let's see, we can turn our ester into a carboxylic acid. We saw that. We could also form a tertiary alcohol. We can form an aldehyde, a primary alcohol, and we could also form a different ester. Esterification. All right, so see if you can fill in all those blanks. Pause the video, and then when you're done, we'll go over it together. All right, so earlier we said that one way we can turn a carboxylic acid into an ester is to use an alcohol and some acid. We also said that we could use sodium hydroxide followed by an alkyl halide. But there is one other way we could do this. We could turn the carboxylic acid into an acid chloride using thionyl chloride, SOCl2, and then we can follow that with an alcohol and pyridine. So you can always go through an acid halide if you get stuck. Okay, how would we make the carboxylic acid on the upper right? So we saw that you could use acid hydrolysis or base hydrolysis. Here, let's just write down acid hydrolysis, but you could also include the base hydrolysis too. Let's see, how would we form our tertiary alcohol? So we said we would need Grignard reagent, followed by water to protonate the alcohol. And what special reducing reagent do we use to make an aldehyde? We use that dibol H followed by water. Okay, and what about our primary alcohol? We would use our usual reducing agent, lithium aluminum hydride, followed by water. And we probably need excess lithium aluminum hydride, although typically we have excess anyway. And how would we perform esterification, where we turn our ester into an entirely different ester? We just use an alcohol. But that alcohol has to have a different R group to make our different ester. Okay, so I know this was a lot for this lecture, but if you look at all the reagents, they're pretty much all the same as what we talked about before, other than that special reducing agent, dibol H. So not too much different here, which is why we kind of went through it pretty quickly. Next time we're going to talk about amides, and then we just have one more derivative after that, the nitriles. So we'll wrap up chapter 20 in a couple of lectures here. So I'll see you in the next video.